Large-scale machine learning. The presentation will be organized in two different parts. In the first one, I will talk about Pythonic tools to perform machine learning, parallel machine learning, large-scale machine learning, and then we will analyze some few examples, 3 case studies of large-scale machine learning. Okay. Basically, machine learning. For this talk, I'm assuming that most of you are at least familiar with some machine learning methods and will know have the time to. I will not have the time to go deeper in the details of the different methods. So no introduction again on machine learning. Machine learning basically is related to data analysis in some sense. It's about predictions on data. And in these talks, we will assume that machine learning should be translated in something like algorithms on data. Okay, so this is the problem. And in particular, we will talk about algorithms on data when we have a huge amount of data to handle. So we need algorithm speed up. Okay, so we need to go fast. We need to analyze data faster and faster in order to be effectively efficient in performing our prediction by machine learning techniques. So the first thing I thought about when I first tried to tackle this problem was, okay, well, algorithm speed up, Python and speed up, sounds quite funny because, you know, we in Python, we may have different languages that could be more efficient in Python. Math processing in Python, could be quite a mess because of the GIL, so the global interpreter lock. Well, but I'm quite sure that after this first part of the talk, we'll start to handle this kind of stuff. Okay. So you should be more and more excited to try the different tools I'm going to present. So we should deal with parallelization. Parallelization indeed could be tackled in 2 different configurations. We may have parallelization on single machine with multiple cores, or multiple machines with multiple cores. And we will describe some few tools for the 2 different configurations in the next slides. So the first case, single machine, multiple cores. The first tool in Python we may leverage for multiple processing is the multiprocessing library. Do you already know this library in Python? Okay. Do you know that this library is already in the standard library of Python? You know. Okay, that's great. Multiple processing is very useful because it tries to tackle with the problem of the GIL with threads. Okay, I have no time for talking too much into details of this, but the problem of threading in Python is basically related to CPU-bound computations. Okay, because you have just one interpreter running on a single CPU. So the problem is, even if you have multiple threads that's supposed to run on different CPUs, in theory, in practice, they run basically on the same CPU because of the GIL. Okay, and this happens basically for CPU bounds and also, only for CPU bound computations, not IO bound. Multiple processing tries to tackle this problem by creating processes instead of threads. So instead of creating multi-threads program, we are going to create multiple process threads. Basically, what multiprocessing does is to instantiate a new version of the interpreter on another core. So has to run a new interpreter instance on another core, and thus the process on that core. It has a very simple API. It's part of the standard library. It has a cross-platform support that it's going to be even improved. Even in the latest version of Python 3.4, specifically Python 3.4.3, included the implementation of spawn instead of fork on Unix. This is really important because of the memory copy and memory allocation related to fork when creating new processes. It has some support for shared memories and support for synchronizations, specifically lock structures. Just a few examples. Multiprocessing. From multiprocessing, we import pool. Pool is the class we use to set how many threads, how many processes we want to allocate. We may call the map. In this case, we apply the type function to every argument in this iterable in this structure, and these are the result. And the computation of each single invocation of type is executed basically on 3 different CPUs in 3 different processes. We may also call the version of map asynchronously, so we don't need to wait for all the computation to end. And we need to call the get method to get the results after the map async invocation. Some cons for multiprocessing: it has a very bad documentation, almost no doc strings in the method, bad support for keyboard interrupt event, and very tricky to use for shared memories values with NumPy structures. We also have joblib. Joblib is a great package which has been basically introduced with scikit-learn, and indeed it has a deeper integration with scikit-learn. Joblib has a transparent disk caching of the output values and lazy re-evaluation. This feature is called memorization. It has an easy, simple parallel. It is used for, of course, single core, multiple cores on a single machine, and it has some logging and tracing facilities for the execution. So I should say that joblib is an extended version of multiprocessing for such computation. The API is quite simple. We need to create a parallel object, and njobs is the parameter that indicates the number of processes we want to allocate. In this case, we want to call the function sqrt on these arguments, and the arguments are the numbers from 0 to 9, and we want to in this case we are declaring the function we want to parallelize, and these are the results. And every time we executed 2 instances of the function on 2 different processors. Moreover, joblib introduced a new parameter in parallel object, which is backend, that is used for trading. Backend trading means that we, instead of using multiprocessing in the background to handle the different processing to run, we may use multiple threads, and we may use this backend to fasten up the computation when we are sure that the code that is running behind, so the code that we are effectively parallelizing, does not suffer the problem of the GIL. This could happen, for instance, when we may execute some NumPy or SciPy code that doesn't suffer for the problem of the GIL because of the C implementation in the background, for instance, for C+ or stuff like that. As I said before, joblib has a deep integration with NumPy, and in particular, if we have this data, we may define this data structure. For instance, we want to create this data structure. We want to serialize on the process we are going to execute. For instance, we may have the dump method to dump the structure in a serialized version, and out of the box this is quite simple with just a call to the dump method, and this is quite useful to serialize the data to pass among the different processes in case we need it. And of course we may pickle the object, and then we may also load the object again in using the mmap mode, which is basically a sort of memory mapped version of the data. So it's binary structure that's which is deeply integrated in the memmap method of NumPy. Moreover, okay, this is the memmap version, and that's fine. Okay, so we might here basically we're okay, we're mapping this file path, and then we might, okay, we're again using the same memmap file to the NumPy, and then pass the memmap structure to joblib, maybe in the next slides. Okay. Moreover, joblib, as I said, is also deeply integrated into scikit-learn, and in fact many different methods included in scikit-learn, such as cross-validation, grid search, random foresters, also support these parameters, which is the number of jobs to allocate for the execution of the method, just out of the box. That's what I mentioned in the talk this morning when I talked about the easy API scikit-learn has about some machine learning methods. So basically, under the hood, if you pass a number of jobs which is greater than one, in the background is using joblib to run the multiple computation on multiple processes for the different methods, in this case for cross-validation, grid search, or random foresters. Of course, not every machine learning method should be parallelizable. It's parallelizable, so should be parallelized. Only those who can have this additional parameters in the API. Then we may have the other configuration setting: multiple machine, multiple core. In this case, one possible solution to exploit is the IPython parallel processing library, which is a great project. I mean, it has an interactive exploratory shell, and it should be used for multi-core and distributed computation. Basically, because of a great out-of-the-box feature that is in charge of load balancing the computation among the different machines working in the background. Setting up the clusters of IPython is quite simple. You need just to run this command. So this command is typed directly in IPython notebook, but it's exactly the same in a terminal shell. You have to digit IP cluster start -n equal 2 in this case, which tells the number of processes we want to run in parallel at each computation, and -- daemon just to tell that the IP cluster process should be run in daemon mode. In fact, in this case, in case we are running in a notebook, or an IPython notebook, we will have a cluster tab that indicates the fact that we are currently having two local clusters with two engines. We have one single clusters with two engines running in the background, waiting for our parallel processing. And this is the code. So from IPython parallel, we import the client. The client is basically the class that we need to handle the computation, so to talk with the different processes in the instantiated cluster. In fact, in this case, with the length of the client is 2, because we have two clusters, actually two processes waiting for our instructions. One of the greatest features IPython parallel has is that it is completely interactive, so we might exploit the IPython magics to control the execution. If we use this magic, we're basically telling that we want to execute on all the processes these instruction and these instruction again. So in this case, we're basically assigning the value of 1 to A and printing A for the two processes running in the background. This magic is just to have multiple lines on the same cell. So in this case, we're basically multiplying A by 2, and we print again A on the two different processes. And in this case, we see that the value of A is copied between the two processes, okay? Because A on the second process is not, for instance, 4, but it's 2 again, okay? Another important feature is the direct view of IPython parallel. We may define this function where mi that support the okay, so we want to know which is the PID of the process we are currently running and the host name of the process. So we apply this function where mi on the two processes running in the background. And in this case, I instantiated 4 different processes, indeed. So the clusters has 4 different processes, and so the host is just the same because I'm running on my local machine, no different host. But the PID of the process running this function, which is sorry, let me show this again. Okay, this is applied asynchronously. Okay, so the function has been, where mi has been applied 4 times asynchronously on the 4 different processes waiting in the background, and these are the 4 different PIDs of the processes running. And getDict is the method to call the dictionary of results for each process. So this is the result we get from the execution of the function on the first process, and this is for the last processes, and that's it. And finally, we may control all the engines running by calling the clients with all with this sort of slicing that takes basically all the processes running. And for instance, we may also apply an input. This is a great function, for instance. We want to sync the imports. So basically, with this instruction, with this context, we're importing NumPy once for all the processes running in the background, okay? So basically we're importing NumPy just once and not 4 times. That's a great feature because it saves a lot of computation. And finally, the load balanced view related to the fact that we may also control by the client object. We may also control. We may also have a view, not a direct view, but a load balanced view that is in charge of load balancing the computation among the processes. Finally, another possible solution we may exploit is the so famous MapReduce approach for multiple cores, multiple engines, multiple machines. In Python, we may have different solutions to implement the MapReduce algorithm. Disco is one of the different libraries you may have. This is just a very few lines of Python to have a MapReduce approach algorithm running. So we run the job, indicating which are the function to map and to reduce. That's very pretty simple and taken from the documentation of the Disco project. But indeed, in Python, we may also have Mr. Job, PyDupe, AppEngine, and MapReduce. Actually, there are many solutions, many libraries to exploit. PyDupe, for instance, is basically directly integrated with Hadoop cluster. So the most famous implementation of MapReduce. Okay, so this is really interesting to try to apply some of this stuff in the in our machine learning computation. How much time do I have? 10 minutes. Okay, well, fun. So some use cases to scale up machine learning algorithm. The first thing we may mention is that parallelizing machine learning use cases could be divided into different categories. We may have, in case of machine learning, we may have embarrassingly parallel machine learning use cases. This means that the computation is basically independent on each of the process it goes on. So that's why it calls embarrassingly parallel, because we may easily parallelize the computation by simply split the computation on multiple machines without worrying about possible shared state or for instance concurrency problems. Okay, this is the case for some use cases. Multi-model assessment with cross-validation, model selection with grid search, or stateless feature extraction. Just in case you didn't realize it, that's why the cross-validation and grid search methods in scikit have the njobs parameter, because the model assessment with cross-validation or model selection with grid search, we will have an example of this in the next couple of slides, but that's why they could be easily, since these are two cases of embarrassing parallelizable machine learning use cases, machine learning applications, processing, you have the njobs parameter, because the computation could easily run on multiple processes without any problem at all. And there are indeed other parallel machine learning use case that requires inter-process communication. Okay, this is the case of in-loop averaged models. We will have an example of this. Since we are quite running out of time, let me try to skip this use case, which is fairly simple. If we have time, we'll talk about this at the end. I would like to point out another problem here. Okay, the second use case is parallel text classification. This is a case of embarrassingly this is a case of inter-process communication. Loop averaging model. So we start by having all the textual data and all the labels to predict. This is text classification, okay? So it's supervised learning. We have the labels to predict. We need to train the model we are going to define for the classification. One thing we might do is try to divide the data in three different sets, into different buckets. Okay, and we all, of course, apply the respective labels to every bucket of the data. For each of the bucket, we might translate the data into their vectorized representation. So the textual data 1 becomes the vectorial data 1, and so forth, so on, so forth, and all the labels respectively associated. For each of the bucket, we may define three different instances for the classification method we're going to apply. Okay, but of course, the classification results depends on the average of these computations. So we're in the case where we are actually collecting the execution of the single instances of the classification on the different buckets, and we're basically averaging the results. So indeed, what we're actually implementing is that we're defining a model which is defined on the average parameters calculated on the different buckets. Okay. Of course, this is not a general. This is just a quite general example, but in this case, you need to demonstrate that the computation for the method you're going to use for the classification will end up in quite comparable results, because not every machine learning technique could be averaged in the final model we're calculating. There is an example with the perceptron model, for instance, using the IPython parallel computation. So basically, we're extracting the features with the feature extraction features included in scikit-learn. Then for each process we have, we're going to parse a bunch of data used for training. These are textual data, basically. So we're reading the CSV file in different partitions, and in particular we have 50,000 of these should be tweets, for sentimental analysis. And in every partition we're going to have 50,000 tweets to analyze. So each process is in charge of analyzing this bunch of data, and then we are calling the perceptron model to fit the data we're going to analyze for each process. So basically we're going to have in case we have 4 different instances of the IPython cluster. We're going to have, we're going to have 4 different computations of the model, in this case the perceptron model. And then yes, we have the output of the first process, the output of the second one, the third and the fourth one. Okay, so after that we need to average. Okay, so this is the computation, the parallelized part, and this is easily recognized by the px magic of the IPython parallel. And afterward we need to gather the results, so we call the gather function, which is a function that should be called after all the processes have been executed. The gather gets all the results from the different perceptron model. In fact, after this function returns the perceptron instance fit with the data we're analyzing in this particular bucket, we gather the results and then we average. Okay, the average linear model basically is the average model we're computing to have the final model on the data analyzed one bucket at a time on different processes. The last example I would like to mention is the model selection about calculating the cross-validation score. Here we have again all the textual data, all the labels to predict. Again, we use the same strategy to divide the data into different buckets. And in case of cross-validation, the problem is use these 2 buckets for training and this one for test. Okay, and iterate the computation by switching the roles of these every bucket, every iteration, or every cross-validation iteration. So we need to have 1 and 2 for training, 3 for test, 1 and 3 for training, 2 for test, 2 and 3 for training and 1 for test. Okay, all possible combinations. And jobs parameter in the cross-val method of scikit-learn perform exactly these computation. In fact, we said that the cross-validation should be applied to 3 different buckets, and we may run these on 4 different jobs. The grid search is another method that supports the same, quite the same strategy, and we may apply this. We see it running. This is about we're trying to estimate the best model parameter for a support vector classification. In particular, we're trying to find the best solution of the classification on the data we have for the C and gamma parameters for SVC algorithm and the values associated in each iteration. For the C parameters is chosen in the log space from -1 to 2 in steps 4, and for gamma in log space from -4 and 0 at step 5. So we applied the grid search, and these are all the possible combination of values we're going to instantiate on the different processes, and we're going to run 4 different processes at a time by the grid search cross-validation in order to estimate the best parameters that produce the best fitting result on the data we have and this is just to find the best configuration parameters we have on the model we want to train. Okay? And finally, these are the final results. The last mention I would like to make, just 1 minute, thank you, is what if the data do not fit into memory? This is another very important problem. So we have data that too huge to be processed in to fit into memory. So we need to tackle this problem. We need to find solution to handle this case, and there are some machine learning algorithm that support. Basically, the idea is try to fit the model by analyzing a bunch of data at a time, and try to improve the fitting process by adding new data at every iteration. This is supported in scikit-learn by a method which is called partial fit, and this is the code to show you the example. For instance, we're going to have the data which are digits. Okay. First of all, please note that these digits dataset is one of the dataset provided out of the box by scikit-learn. We split the data. Basically, digital digits is a dataset of images that have been used to train a classifier in order to their images of handwritten digits, and we want to train a classifier in order to make the classifier able to distinguish among the different digits from 0 to 9 displayed in the images. Okay, it's basically related to handwritten recognition problem. Digits is a data set of images of digits and corresponding number, so the corresponding labels. We split the data, and finally we load the data serialized into pickle file here by using the aforementioned joblib load function. And the joblib load function basically what does is to transform the pickled file into 4 different NumPy structures memory mapped. So it's very useful for this kind of computation. Again, we want to train a support vector classifier model. We want to apply the grid search, but basically, so the grid search function is going to apply the evaluation of the in parallel, the evaluation of the fitting function on every bunch of data we're going to use for every possible parameter configuration. But the compute evaluation function is the one we want to point out. That's because the split, the dimension of each splitting should be could be too huge for the memory we have. So we might use the fitting function, which is okay. Let me go to the partial fit. Okay, so sorry. So the partial fit here is that this one. Okay, so basically we might use the partial fit function to partially fit the model every iteration at a time. And basically what we need, or what we have, sorry, is that for every single iteration, the performance, so the efficiency of the model we're training is improving better and better. Of course, this is a graphic that displays the number of samples over the validation score we get. So this is quite important. We might speak a lot about this, but the point here is that we're improving the performances of the model we're training by training the model considering one bunch of data at a time. Okay, and again, this method could be leveraged only on specific machine learning methods. Okay, but in case we're going to have the partial fit function, we should leverage it. And that's conclude my presentation. Thank you for your attention.
Okay, thank you, Valerio. We have only 1 minute for a quick question.
Grazie. Una domanda. Allora, supponiamo che io privato abbia inglese?
English, please.
Allora, suppose that I am a client, okay? I need to analyze a lot of data, okay? I search for a library, I choose a multiprocessing pool, okay? Now, I need a lot of processing memory. I choose a cloud computing service like Amazon, DigitalOcean, and I pay for a tot of core, a tot of thread for a specific time, like a week, okay? There is a way with multiprocessing or another library to check if for all the time of the execution of my script, the the processing potential is constant.
Constant in resource usage.
Yes.
Okay.
No,
So you basically want
research
to.
offered by the service. If I pay for a 16 core, I want 16 core, not 60 thread.
Okay.
There is a way with multiprocessing to check.
Okay. Actually, there is an integration I forgot to mention, so thanks a lot for pointing this out. IPython Parallel is deeply integrated with Star Cluster, which is our cloud services providing computational resources. So you might run your IPython cluster in a cloud computation engine. And you may leverage IPython cluster to control the resource usage you're going to use. About your question, so you want to control the number of cores you're using, basically. But well, when you run multiprocessing pool or IPython clusters, you're basically defining the number of processes at most you want to execute. If you don't need it, you don't use it. That's it.
Okay, thank you very much. If you have other questions, please do outside with the speaker.
Thank you very much.